Every force in the universe comes in pairs. When two particles pull on each other, each force does work, and you might expect the bookkeeping to require tracking both bodies separately. It does not. This appendix proves a remarkable result. The total work done by an interaction pair depends only on the relative motion of the two bodies, governed by a single effective mass called the reduced mass. Start with the setup. Two bodies, 1 and 2, interact through a Newton's third law force pair. Body 1 feels the force F21 exerted by body 2. Body 2 feels the force F12 exerted by body 1, equal in magnitude and opposite in direction. Choose an origin and draw the position vector R1 to body 1 and R2 to body 2. The vector we care about is the relative position, R21 defined as R1 minus R2. It points from body 2 toward body 1. As the bodies move, body 1 shifts by the small displacement dr1, and body 2 shifts by dr2. Write Newton's second law for each body separately. Body 1 has mass m1, so the force F21 equals m1 times the second derivative of r1 with respect to time. Body 2 has mass m2, so F12 equals m2 times the second derivative of r2. That is two vector equations describing two coupled motions. The strategy is to merge them into one equation for the relative position alone. Divide each equation by its own mass. The first becomes F21 over m1 equals the second derivative of r1. The second becomes F12 over m2 equals the second derivative of r2. Now subtract the second equation from the first. The right side becomes the second derivative of r1 minus the second derivative of r2, which is exactly the second derivative of the relative position r21. That is the relative acceleration of body 1 with respect to body 2. One subtraction has turned two equations of motion into a single equation for the relative coordinate. The left side still contains both forces. Newton's third law removes one of them. F12 equals negative F21, so minus F12 over m2 becomes plus F21 over m2. The left side is now F21 over m1 plus F21 over m2. Factor out the common force. The result, F21 times the quantity 1 over m1 plus 1 over m2, equals the relative acceleration. A single force now drives the relative motion. The sum of inverse masses appears so often it earns its own name. Define 1 over mu as 1 over m1 plus 1 over m2. Combine the fractions over a common denominator. 1 over mu equals the quantity m2 plus m1 over m1 times m2. Invert both sides and the mu equals m1 times m2 divided by m1 plus m2. This is the reduced mass of the system, and the name fits. Mu is smaller than either individual mass. Check two limits. If the masses are equal, mu is half of either one. If m2 is enormous compared to m1, the denominator is dominated by m2, and the mu approaches m1. The light body does all the moving. Substitute the definition. The combined equation becomes F21 equals mu times the second derivative of R21. Compare it with the familiar law for a single particle. Force equals mass times acceleration. The structure is identical. The two-body problem now looks like one fictitious body of mass mu, moving along the relative coordinate under the single force F21. Every tool built for one-body motion applies. Now compute the work. As the system evolves from an initial state A to a final state B, each force acts through its own body's displacement. The total work is the integral from A to B of F21, dotted with dr1, plus the integral of F12, dotted with dr2. By the work-energy theorem, with no external forces acting on the system, this total work equals delta K, the change in the kinetic energy of the system. Two integrals, two paths, two bodies. Watch how the third law collapses them. Replace f12 with negative f21 in the second integral. The sum becomes the integral of f21 dotted with dr1 minus the integral of f21 dotted with dr2. Both integrals now share the same force, so combine them. The integral of f21 dotted with the quantity dr1 minus dr2. That difference of displacements is dr21, the relative displacement. Here is the key insight. The work done by the internal pair depends only on how the separation between the bodies changes. If the two bodies translate together rigidly, the relative displacement vanishes and the pair does no net work at all. Substitute the one-body equation for the force. F21 equals mu times the second derivative of R21, so the work becomes mu times the integral from A to B of the relative acceleration dotted with dr21. Next, convert to a time integral. The differential dr21 equals the time derivative of r21 multiplied by dt. The work is now mu times the integral over time of the relative acceleration dotted with the relative velocity. That combination, acceleration dotted with velocity, is the signature of an exact derivative. Here is the identity that finishes the calculation. Take the relative velocity dotted with itself and differentiate with respect to time. The product rule gives two terms, the acceleration dotted with the velocity plus the velocity dotted with the acceleration. The dot product is symmetric, so those two terms are equal. The derivative of the velocity dotted with itself is therefore twice the acceleration dotted with the velocity. Divide both sides by 2. 1/2 of that time derivative equals exactly the integrand in our work integral. The integrand is a perfect derivative, ready to integrate. Substitute the identity into the work integral. The work equals mu times the integral from A to B of 1/2 times the time derivative of the relative velocity dotted with itself. Integrating a derivative just evaluates the quantity at the endpoints. The work equals 1/2 in mu times the relative velocity dotted with itself, evaluated at state B minus the same expression at state A. Write V sub B for the relative speed in the final state, and V sub A for the relative speed in the initial state. The work done by the interaction pair is 1/2 mu times the quantity V sub B squared minus V sub A squared. The labels 1 and 2 were arbitrary, so the answer must not depend on them. Check it. Exchange the two bodies everywhere. The force F12 is negative F21. The relative position R12 equals R2 minus R1, which is negative R21. Its differential flips sign the same way, and the relative velocity V12 is negative V21. Now look at the work integral. It is a force dotted with a relative displacement, and each factor flips sign. Two sign flips cancel. In the final formula, the relative velocity enters squared, so its sign flip cancels as well. Either labeling gives the identical work. The result respects the symmetry of the third law that produced it. Now assemble the physical statement. The work done by the internal force pair equals the change in the system's kinetic energy of relative motion. Delta K equals 1/2 mu times V sub B squared minus V sub A squared. Read what this says. Internal forces cannot change the motion of the center of mass. They cancel in pairs. The total kinetic energy of the system splits into two pieces: the kinetic energy of the center of mass and the kinetic energy of relative motion. Internal work touches only the second piece, weighted by the reduced mass. A stretching spring, two colliding cards, a vibrating molecule. In every case, the internal work shows up entirely in the energy of relative motion. This result closes the chapter and it completes a pattern. Chapter 13 began with energy itself, the ledger that never changes, where the energy transformations inside the system and its surroundings always sum to zero. It narrowed next to the kinetic energy of a single particle. Net work equals the change in 1/2 mv squared. The machinery grew from there. Work by constant forces, work by varying forces as an area under a curve, power as the rate of doing work, the dot product, the line integral of force along any path, and inverse square forces in 3 dimensions. This appendix extends the theorem one final step to a system of 2 particles. Even the work of internal forces obeys the same law, with the reduced mass mu standing in for m and the relative velocity standing in for v. That substitution is the doorway to the two-body problems ahead: orbits, collisions, vibrating molecules, where one imaginary particle of mass mu carries all the physics of 2 real ones. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.